Okay, so this video will start chapter 5 on magnetostatics, and you will learn how to calculate magnetic forces on current carrying wires placed in a magnetic field and the torque exerted on that. And then we'll also learn two techniques on how to calculate the magnetic fields based on the current distributions. So the first part will look at forces due to existing fields in space on current carrying conductors, and then the second part will see how also to calculate the magnetic fields due to the current distributions. We'll look a little bit also into magnetic properties of materials, and specifically magnetic hysteresis in ferromagnetics, and we'll see how to calculate the inductance of simple structures like a solenoid, coaxial transmission line, or other symmetric type geometries. And lastly, we'll see how the magnetic energy stored in a region is given by is related to the magnetic field in that region, just in the same way as the electrostatic potential energy is related to the electrostatic field in the region. So there are many parallels between electrostatics and magnetostatics that we can see looking at the governing equations, which are Maxwell's equations. And starting from the sources, we can see that for electric field, the sources are charges, whereas for magnetic field, the sources are charges in motion or currents. The fields and fluxes that help us take into account the effect of materials are E and D in electrostatics, and H and B. And E and B are the actual total electric field and magnetic field that are measured in volts per meter and in Teslas for magnetic field. The material properties that determine the total fields within materials are the electrical permittivity and electrical conductivity for electrostatics, and magnetic permeability for magnetostatics. And one important difference that we'll see is that whereas matter always decreases the total electric field, it can decrease or increase the total magnetic field. Now if we look at Maxwell's equations, we see the divergence of electric field is given by a volume charge density, rho v, and if we deal with D, is the free charges. If we look at E, is the total charges per volume divided by epsilon naught, whereas divergence of B is always zero. So what this means is that there are no isolated or point sources of magnetic field. And we'll see in a little while that magnetic fields are always form closed lines. They do not start and end anywhere. So that's the meaning of this divergence being zero everywhere. And that's a fundamental result that has not been proven wrong so far. There have not, no one has identified magnetic monopoles or sources, point sources of magnetic field. Then the curve is zero in electrostatics, and for magnetostatics the curve of the magnetic flux density H is given by the current, which are the sources. So these are sort of swapped in electrostatics and magnetostatics. It's the divergence of B that is 0, and it's the curl that is given by the sources. And these equations can be expressed in the integral form by applying Gauss's theorem and Stokes' theorem, as we saw for electrostatics. And remember, these are like this because we are dealing with statics, so we have dropped the time derivatives in Maxwell's equations to this set of decoupled pairs of equations. So we can fully solve for electric fields if we know the charge distribution, and we can solve for magnetic fields if we know all the current distributions. There's a scalar V because the electric field is conservative, the curve is 0. We can define a scalar function V, the gradient of which is the electric field E. And for the magnetostatics, the vector, there's a vector quantity that we can relate to the magnetic field also by a space derivative, but it's the curl now of the potential that gives us the magnetic field. The energy density in electrostatics, we saw this for a capacitor, but it will be shown later that this is a general result for any configuration. The stored energy density in electric field is 1/2 epsilon E square, and in a similar way for magnetostatics is 1/2 mu H square. And electric force is charge times field, magnetic force is charge times velocity cross the magnetic field. And in terms of circuit elements that are used to model the electrostatic and magnetostatic effects, we talked about capacitance and resistance in electrostatics that relate charge, voltage and current for a certain element, or capacitance for two conductors. So for magnetic field is the inductance that relates the voltage and current for a given element, a given physical structure, where we can apply a voltage and see current flowing through. So magnetic force has this, whereas the electric force is always parallel to the electric field, magnetic force is always perpendicular to the magnetic field. And also interesting, that was puzzling for a long time when these observations were being made, was that there's only force if the charges are moving. So electric force affects any charge Q in the presence of an electric field E, whereas magnetic force only affects charges in motion. So only charges in motion, it's perpendicular to B, and because of that, the work of the magnetic force is 0, because it's the linear path integral of force and displacement, because the velocity is parallel with the displacement. the force is perpendicular to the displacement, so it's always 0. And we can write the total electromagnetic force then as the electric plus magnetic as QE plus QU cross B. And this is called the Lorentz force. And as you may probably remember from physics courses, the directions are or can be found using a right-hand rule, which is the general case for any cross product. So when you cross, there are many ways of doing this right-hand rule, but you can, if you have your fingers with the first vector turning towards the second vector, then your thumb will point along the result. So here on this gray plane, if charge Q is moving along this blue arrow velocity, and we take the cross of velocity to magnetic field, you see that the force is going to point along the red arrow for this positive charge. Okay. Here at the bottom we have a upward pointing magnetic field, so if a negative charge is traveling to the right and you take the right hand rule U cross B, the force would be in this direction for a positive charge and in this direction for a negative charge. Charge times velocity is a current, so we can write the magnetic force in differential form as the current times the displacement vector, because we still need to keep our direction, that gives us the velocity. So we can write U as the magnitude of the velocity along this dl dt would be the velocity, and the charge divided by dt is our current. So we have the L cross B. So one thing we can see from writing it in this form is that if you take a closed line integral of this force, the result is always 0. So for a closed circuit carrying a current I, the total magnetic force is the L cross B. So because the dl part for a constant field, we can take the field out, and we see that this force should be 0 because this is going to integrate to 0. So this is only true for when we can take this out of the integral, which is a uniform external magnetic field B. Okay. So if the film is changing, then it will depend on how it changes along this current carrying wire. And here we can look again at directions. So if you have a flexible wire, a vertical wire, like in these diagrams, without any current, the wire does not experience any force. If we apply a voltage potential so that there is current flowing upwards, we have our velocity times B, so the force is to the left. And the same if we have a velocity downwards, now the force is to the right for positive charges, which is the definition of the current direction. So a current downward like this represents positive charges moving downward. It may be that the charges in that material are negative, so that would correspond to negative charges traveling upward. Okay, and the other important maybe mechanical concept that we'll talk about related to magnetostatics and that will apply to generators is the idea of torque. So if a force acts on an object that is fixed but able to rotate about an axis, this quantity torque, that is the arm of the force, the times the force gives us the torque, which is a measure of rotation and the magnitude and direction. So in this case here, if you have this disk about this axis z that is free to rotate, and if we apply this red force, you can see that it's going to rotate in this direction, which also, using the right hand rule, corresponds to a torque along plus z, where you take the moment arm is perpendicularly from the axis to the point where the force is applied, and when you take the cross product of that, you get this force in this direction, the torque, sorry, in this direction. And this torque concept is important because in situations like a current loop in a uniform field, as we saw, we know that the total magnetic force is zero, but that does not mean that the torque is zero. So if a situation like this, where we have the current going in the blue, so looking at this upper right diagram, current going in we call this the counterclockwise direction, because it's opposite to the clock direction. And we have a uniform magnetic field from left to right. If we look at our magnetic force, I L cross B for a straight segment. So we had the differential force with the displacement vector. If this is a straight segment, we can write it as I L cross B. So here we can see that segments 2 and 4, B and L, are either parallel or anti-parallel, so the force is 0. Then on 1 we have L, our vector L pointing down, B pointing to the right. So the force is out of the slide, which we represent by this point. Think of an arrow pointing at us, so that's the force. Whereas in segment 3 we have L pointing up, B, our uniform B, still pointing to the right. So the force, when you do L cross B, the force is into the slide, which we represent with this, in this arrow notation, by a cross in a circle. So we have F1 out of the slide, F3 into the slide. They have the same magnitude because the current is the same, the length is the same, and the magnetic field is uniform. so they add up to 0, there's no net force. But if this is a loop that can rotate about its axis, then these forces add up to a non-zero torque that will make this loop rotate in this direction, because this force on the left hand side is pulling it out of the slide, the one on the right into the slide, so this will rotate in this direction. And if this axis is y, like here, and we take the cross products, we see that this rotation corresponds to a plus y torque. So again, follow the right hand rule, and a plus torque, it's this rotation. A plus y torque is if you look down on the loop from the positive y-axis, we will see a counterclockwise rotation of the loop. We started by looking at the straight perpendicular loop to the field, which gives us the maximum magnitude of torque, but this loop may be at any angle, and actually as soon as it starts moving it will be at an angle, and we have, in order to calculate the dynamic torque on the loop, we need to account for this angle that the loop is at with respect to the magnetic field. And in order to calculate or name these different components, we use a magnetic moment of the loop, which is given by the normal vector to that loop. So in the case of our perpendicular loop, the normal vector to this loop would be the plus z, so out of the slide, and again following the right hand rule for the current. So if the current is going like this, the normal to that loop is out of the board or out of the slide, and that's called the magnetic moment, and it's the current times the area and with this direction of the perpendicular vector to the surface of the loop. And because in this case there can be, if it's an open plane, we don't have an outward direction to be uniquely defined, so the convention is to use the right hand rule to call this a positive or negative magnetic moment. Okay. And when you express it like this, then we can calculate the torque, and this factor of the sine comes in if we say that the torque is given by the cross product of the magnetic moment times the magnetic field. So in our case of the perpendicular loop to the field, the torque was just the area of the loop times the current times the field, which is the magnetic moment. Because they were perpendicular, so the sine was 1, but in general, and whenever the loop starts moving, we have to account for this decreasing magnitude of the torque, and that is done by taking the cross product of this magnetic moment with the magnetic field. And here at the bottom we have the a top view looking at this from the positive z-axis down, we would see these orientations of the different forces. The magnetic field to the right along plus x, and we'll see that the loop in this case is going to turn in this direction, which is along negative z. So here our torque at this moment would be along minus z.